What's up everyone? Today we'll be taking a look at the Quicksort algorithm. So the Quicksort algorithm was developed in 1959 by Tony Hoare while he was in the Soviet Union. While working on a project on machine translation, he needed to sort the words of Russian sentences prior to looking them up in a Russian English dictionary that was already sorted in alphabetical order. So he recognized that insertion sort would be slow, and therefore he quickly came up with a new idea that was quicksort. Then Robert Sedgwick's PhD thesis in 1975 that was on the study of quicksort spurred even more improvements to the original quicksort's algorithm, such as for dealing with extreme cases, tackling problems of a good pivot solution, and new variations of the quicksort algorithm was also invented to optimize the sorting time. And examples of such variants are sample sort, adaptive partitioning, and the dual pivot quicksort, which we will be discussing about later on. Alright, so now let's find out how this algorithm works. So the first step of the algorithm is to select a pivot, which is the element to be used for a reference of comparison. Since how quicksort works is by placing elements smaller than the pivot to the left of the pivot and placing elements larger than the pivot to the right of the pivot. And in fact, what I've just said is actually the next step of the algorithm, which is partitioning. Then finally, the last step is recursion, where a new pivot in the left and right subarrays will be chosen subsequently after a round of partitioning. Then partitioning will happen again for the subarrays. Now, I'll be guiding you through the steps of the algorithm using a worked example. So for simplicity, we'll be taking the last element in the array as the pivot. Also, we'll define the wall element as the element immediately on the right of the wall, and over here the wall element is the 0th position element. Finally, we also define the variable j as the counter to iterate through the array. So now let's start. As discussed earlier, all elements will be compared to the pivot, so we do that by moving up the array with j. Now since 7 is greater than 1, we will increment j as 7 is already on the right of the wall. So yeah, we move on to 2. So this goes on for 2 as well as all the elements up till 12b as j increments. So once the pivot is reached, it will swap position with the wall element. This completes one round of partitioning, and we see that the green element is where it will be in the final sorted array, while the blue elements are the right subarray. Since there is nothing on the left of the wall, there is no left subarray. With that, we'll move up the wall by 1 to the immediate right of where the pivot was after it was swapped. Now, the new pivot is 7, which is the last element of the array, and since 2 is less than 7, we shall swap the j element with the wall element and increment wall by 1. In this case, 2 is already the wall element, so no swap was made. Then we see that the remaining elements are larger than 7, so once again it will increment to the second last element in the array without any swaps being made. So that will bring us to another round of partitioning done, and we will swap the pivot and the wall element again. So now we see that there is a left subarray of size 1, the pivot in the correct order, and the right subarray. But since the left subarray is size 1, it means that it is also in the correct position. So this means that 1, 2, and 7 are in the right order in the array that will be output in the end. So needless to say, the partitioning continues. And now we have a right subarray of size 1 and a left subarray of size 4, which are the yellow elements. So similarly, we will only need to work on the left subarray this time round. So when we reach 12a, we actually increment j since we only put elements smaller than the pivot in the left subarray. So with the comparisons done, we will swap the pivot again, and now we have a right subarray of size 3. And of course, partitioning occurs again. Eventually, we reach a point where one of the subarray is size 2, and in such cases, we can simply compare the two elements and swap them accordingly without doing a partitioning step again. So with that, our sort is complete, and here is a detailed explanation of the partitioning technique. So a sorting algorithm is said to be stable if two equal objects appear in the same order in the sorted output as they appeared in the unsorted input array. And as seen from the example just now, quicksort is generally not a stable sort since the order of appearance of objects are usually altered after the sort is completed. As you viewers are all smart people, you might have inferred by now that choosing a good pivot is actually very critical as to how efficient a quicksort will be. So the quicksort algorithm used to sort the example earlier was actually the Lomuto partitioning scheme, where the last element in the array is always chosen as the pivot. So such a pivot selection is actually very unwise as the resulting right and left subarrays tend to be very unequally divided, as we saw from our example just now. Ideally, the pivot should be the median of the array for more equal division of the subarrays. Actually, a commonly used pivot selection method is the median of tree, where we find the median of the first, middle, and last elements of the array, and we use that median as the pivot. So what we are doing is that we hope for this median to be close to the real median of the list, and this is more likely to be true as the list gets more sorted towards the end of the algorithm. Great! Now, let's look at an example of the implementation of a quicksort algorithm using the median of tree scheme. Like most quicksort algorithms, it consists of mainly three functions, two of which are helper functions for the actual recursion function. So firstly, we have a simple method that is used for swapping the position of the elements. Secondly, the next function is to find the median of tree of an array, and the parameters of this function is the array to be sorted as well as the position of the first and last element. What happens next is that the method puts the median at the end of the array, the largest element in the middle, and the smallest at the front. Last but not least, we have the function for the partitioning step and the recursion step, whereby the quicksort will be executed on the subarrays produced. While you might know that quicksort is a fast algorithm, let's take a look at the time complexity. So the worst case analysis of quicksort will be done using a naive pivot selection, such as selecting the last element, and this usually results in the time complexity being O(n squared). And this mainly applies for an already sorted list because the last element will need n-1 comparisons and the second last element will need n-2 comparisons and so on. So on a reverse sorted list, it is even worse as there will be many comparisons and at the same time there will be at least n/2 swaps done. On the other hand, the best case analysis will be done using the median of tree scheme, and the resulting time complexity is O(n log n). And this is because each recursive call calls half of the list, so there will be 2 times log n calls made in total. Subsequently, each call will make a maximum of n comparisons and n swaps. Hence, the overall time taken will be O(n log n) time. So as for the average time analysis, is actually requiring a rigorous proof, so we will not go into that for today. In general, it can be shown that it is closer to the best case, meaning that it is also O(n log n). So we mentioned the variant of quicksort earlier, so now let's take a look at the dual pivot quicksort. So in 2009, Mr. Vladimir actually proposed the new dual pivot quicksort implementation. His implementation was actually chosen as the new default sorting algorithm in Oracle's Java 7 runtime library after extensive empirical performance tests to prove that it was the most efficient quicksort variant. Of course, its time complexity still degrades to O(n squared when sorting the worst case arrays, essentially when the array is already sorted or partially sorted. So now let's take a look at how this quicksort variant actually works with this simulation. So the idea of the dual pivot is that it will have two pivots to compare with, typically selected by the median of 5 pivot selection scheme, and in this case they are the two pivots are the blue and yellow bars. So elements that are smaller than the smaller pivot, the blue pivot, will be placed in the left subarray, the purple elements, while the elements that are larger than the larger pivot, the yellow pivot, will be placed in the right subarray, and these are actually the red elements that you see in this simulation. So finally, elements that are in between these two pivots will be placed in the middle subarray, the green elements. As per normal quicksort, the dual pivot quicksort will then be executed on each of the subarrays. So that's all we have for now. Hope you enjoyed this lesson, and let's get sorting.